Okay, just a few things here to sort of review and also to introduce. This is an overview for the whole course. We start with a population right here. That is everything in which we have an interest. So it might be all students at the university, all residents of Russellville, all residents of the United States. Anyway, that's the large circle here, and all the yellow dots are just individuals within that population. We take a sample from that population. That's the circle in here. So we take a sample. Of course, if it really was a random sample, that would come from all over the place in here, but just for illustrative purposes, we'll put it this way. This is the sample again over here, the data. That is our sample, and from that sample we will do exploratory data analysis, which just includes things like compute the mean of the sample, the standard deviation, the median, also draw histograms, box plots, and so on. A little later in the class, we'll start working on probability, and that's really the theory part of the course, and coming out of that, we will be able to use the descriptive statistics we get here and our knowledge of probability to help us either estimate or test hypotheses about population parameters such as mu. Well, we won't really test them in this course on sigma, but you could. Rho, the population correlation coefficient, and so on. Okay, in this table, just an overview of some of the symbols and concepts that we use throughout the class. First of all, at the top here, we have parameters. Those are characteristics of the entire population. And then we have statistics. These will be characteristics of a sample. If we have a categorical variable or qualitative variable, we will calculate the sample proportion p hat in order to estimate the population proportion p. If we have a single quantitative variable or numerical variable, we will compute from the sample the statistic x bar and use that to estimate or test a hypothesis about the population parameter, in this case the population mean, mu. If we have two quantitative variables, we will compute the sample correlation coefficient, r, in order to estimate or test a hypothesis about the population parameter for the correlation, which is rho. For now. Okay, one of the things that we want to make sure we distinguish between is random sampling and random assignment. These have to do with when you can establish cause and effect relationships and when you can generalize to the larger population as a whole. If you have random sampling, that is, you sample individuals from the entire population, you can make inferences about the entire population. If you have, and that would be an observational study, just put a note there for observation. See, I'm not very good at that. If you have an experiment in which you can use random assignment, now you have individuals and you can assign them to different groups and treatments and placebos or whatever you have there. It could be more than one treatment. But if you have random assignment, then in a true experiment, you can make a cause and effect relationship. So if you have random sampling, you can draw inferences from the population. If you don't have random sampling, you could have sampling bias, and you shouldn't be making inferences about the entire population. If you have random assignment, which you would have in a true experiment, you can make a cause and effect relationship. But if you do not have random assignment, if you don't have experimental data, then there is potential for confounding variables. Ideally, you would have both random sampling and random assignment. Don't have it very often, but if you did, you would randomly select individuals from the entire population and then randomly assign those to groups. So by random sampling from the population, you can have inferences, and by randomly assigning, you can have cause and effect. We often have to make a choice between those, and there's some trade-offs there.